So in this tutorial, we'll be mapping the cross-correlated network of residue-wise atomic fluctuation in an intrinsically disordered protein, amyloid beta 42, the IDP that's responsible for causing Alzheimer's disease. So we will be investigating intrapeptide communication network to derive features of dynamic correlation between all atoms in an IDP. That is the degree to which they move together. This will allow us to investigate the concerted or correlated dynamic changes of the system over time to identify long-range interactions which are not only functionally relevant but also may provide some information about allostery or regulation at a distant site, and is also useful in defining the binding regime of IDPs. So thus, in order to carry out this analysis, we will need to have some prerequisite software packages and files that will be used as an input. So firstly, the R programming language, which is a free software for statistical computing and graphics. So a bit of familiarity with the R programming language is desired, but you can always follow the tutorial and get an idea about how to do the analysis. So you can download the R package or the R programming language from this website, which is the CRAN R project. And the home page will show you the download links for different operating systems like Linux, Mac OS, and Windows. So if you want to download it for Windows, just click on this link and then go to install R for the first time if you're installing it for the first time, if you don't have it already. Once you click on that link, it will ask you to download the R package for Windows. So that's pretty straightforward. So the next thing that we'll need is the R library or package Bio3D that's developed and maintained by Barry Grant and his group at UCSD or University of California, San Diego. So this R script that is written in Bio3D is what we will be using for doing the dynamic cross-correlation network analysis, and the method that was originally developed by Luthi Schulten and his co-workers. So Bio3D approach for this network analysis excludes the long-range correlations between residues that are not in physical contact. So we can install this once you are in the R environment, that is once you have installed the R programming language. You can go inside there and just type in this command install.packages bio3d dependencies is equal to true, and it will do it for you. It will ask you for a mirror from CRAN and it will do the installation for you. So there are other instructions as well on this website, like additional helpful guide and how to cite this Bio3D if you're using that in your research. So it's a very, very efficient program, not only for dynamic cross-correlation network analysis, but for doing a whole lot of other kinds of analysis. So there's a full tutorial dedicated for network analysis on the Bio3D website if you wish to have a look in your spare time. So I have provided this link out here. And you can go through this page and it will give you the step-by-step process of how to generate a network and visualize it, and how to get the information from the trajectory data and then analyze and produce the cross-correlation maps and do the path analysis and stuff like that. Okay, we'll go into the details of that in a bit. But before that, the additional files that we will be requiring for this session is the two input files. The first being the trajectory containing the ensemble of amyloid beta 42 structures generated from running a molecular dynamic simulations to be used as an input for this Bio3D program. Since this is a dynamic interaction, therefore the dynamicity of the protein has to be taken into account. So the trajectory file that we will be using is the concatenated file for 10 models that were produced as an output from the CapsFlex web server in the previous tutorial that you will find. So this is basically the 10 different models that were generated by the coarse-grained modeling method, or running a coarse-grained molecular dynamic simulation by using this server for amyloid beta 42. So this ensemble of 10 different models that were generated by this CapsFlex web server will be used as an input to the Bio3D package or the Bio3D program that we'll be using for dynamic cross-correlation network analysis. However, the format for this file has to be in DCD, which is basically single precision binary Fortran files, and is read by VMD or another program or another MD engine called NAMD here. So we will have to convert those 10 models into the DCD formats, and we'll see that in a minute. And lastly, as an input, we will need a PDB file containing the extended coil structure of amyloid beta 42 that is the one which we generated previously using NMR utility program or the web server from Bax Group. So before going into the details of the programming and before exploring those program files written in R scripting language, let's have a quick look at this tutorial. So we will see that there are two components to build a cross-correlated network model. So first is generating the network model. So if we scroll down further, and we'll come to a point where, so these are all the descriptions of the community clustering method and the different methods and different approaches that you can take to build the network. Starting from here, so the first thing is network generation. So building the network or constructing the network from molecular dynamics data. That is the input files that we'll have. And the second thing that we'll be doing is the path analysis or analysis of the paths after generating the network. So you can visualize the network, and based on the layouts and everything, and you identify the nodes and the communities and the edges, and you have different color settings as well. And finally we reach a state where we do the path analysis, starting with the network node centrality and also the suboptimal path analysis, and that'll give you a fair bit of idea about the propagation of disorder, let's say, in case of amyloid beta 42, since it's an intrinsically disordered protein, and also a whole bunch of other information that will be useful for deriving certain features of the aggregation pathway, let's say. We'll have a look at that as we go along in the tutorial. Okay, so let's dive right into the details of the network analysis of amyloid beta 42 intrinsically disordered protein by using the R scripts. So all the procedures from now on will be performed from the bash terminal here, including setting up the DCD trajectories by concatenation or joining of different models forming an ensemble, to running the R scripts by calling the Bio3D library. So if you are running these in your Windows machine, you can run R scripts by using the RStudio software. So you can download the RStudio software and have Bio3D, the library, installed in it. So as you can see, I have made two different directories or folders. The first is the models directory. So if you list the models here, which you can see above as well. So all the 10 models that were generated as an output from CABSFlex2 will be used as an input after joining them together to form a trajectory. So they'll be used as an input for the R scripts that we'll be using for dynamic cross-correlation network analysis. And the other directory that you see on the left is the DCCNA directory, which is the short form for dynamic cross-correlation network analysis. So if I list this directory here, you'll find two different R scripts. The first one is for constructing the network maps, that's the DCCM.R, and the other one is for the network path analysis. So all the programs that are written in R will end with an extension of .R here. So this directory also contains another model here, which is the PDB file for the extended random coil structure for amyloid beta 42 that we obtained initially from the NMR utility web server. So the first thing that we'll do is set up the input files that will be fed into the R scripts here. So the two input files that we are concerned about are the initial PDB structure file, so that acts as a structure file, along with the trajectory file that will be written in DCD, and that can be read easily by VMD program. But in order to generate the DCD file, we have to combine all of these models together such that it creates a trajectory of 10 frames. So you can see the models start from number 0 until 9, which means there are 10 different models, and they'll be joined together in order to form a trajectory in DCD format containing 10 frames. So we can achieve that by using a command called mdconvert. Okay, so but since I want to keep all these input files inside the directory from where I'm going to run these R scripts with Bio3D, so I'm going to have these input files here in this directory itself. So in order to do that, I will perform the operations on this directory from the other directory. So you'll see that in a minute. So the mdconvert program can convert between different file formats, especially the trajectory file format. So you have the XTC file format for the GROMACS outputs, and you have the DCD file formats for the outputs that are generated with the MD engine or the molecular dynamics package called NAMD. And there are other outputs as well. So AMBER is another molecular dynamics package which produces different kind of output file format with a different extension. And it also has the capability of joining together different PDB files to create a trajectory output as well. Okay, so in this process, in this cross-correlation network map, the correlations will be represented for each of the residues in the peptide. So it's a random coil structure for amyloid beta 42, so it has 42 residues. So for each of the residues, there'll be one representation. So it's kind of co-screening, but then again, it's not really combining all the atoms in the residues together, but representing each residue with that of the C alpha atoms, that is the backbone atoms. So we need to have the input files as well, this PDB file and the trajectory file that we will generate in terms of the C alpha atoms only. So such that you end up with 42 different atoms for the PDB file and 42 different atoms for the trajectory as well. So for each of those atoms, we will generate a cross-correlation map, and then we will perform cross-correlation network analysis, and we generate the network paths, and we analyze the paths for each one of them. In order to achieve that, we will have to define the atomic indices for the C alpha atoms that is in each of these model PDB files. Let's say we open one of the models, so model 0, the very first one, .pdb, and you'll find that the atomic indices are represented by the second identifier. I do not call this column again, so this might be altogether a different column. So let's call it an identifier. So just next to the atom records, the next identifier that you have here is the atom indices. So these are basically the atom numbers, as you can see from here. So we have to pick the specific atom numbers which are represented by the C alpha atoms or the Ca out here. So for the first residue, you have a Ca. For the second residue, you have a different Ca. The atomic index for the Ca of the first residue is 2. The atomic index for the Ca of the second residue is 10. Well, this peptide has only 42 residues, so you might as well argue we can just, look at this file and then copy these numbers, or write down these numbers in a separate file. But how about if you have a bigger protein? Let's say you have a protein alpha-synuclein which has 140 residues. It would be very cumbersome in order to copy each one of these atomic indices. Let's say for residue number 40, it's 300, the atomic index. So in order to fast pace this process, or automatize this process, we'll use another scripting language called the awk or AWK. So awk is a very powerful domain-specific language that is basically designed for text processing. So if you open model 1 as well, you'll find that the atom indices for each one of the residues are in the same position as that of model 0 there. So the C alpha for the first residue is at atomic index 2, and the C alpha for the third residue is at atomic index 15, so on and so forth. So we'll pick these numbers by using an awk script. Awk is a one-liner script, so you can just have one line written here of the script, and it will perform the operation for you on that particular file of the PDB file of the model that you're interested in. And we can operate from this directory here, because this is the directory from where I'll be running the cross-correlation network analysis, the R scripts with Bio3D. And we'll be operating on the file on a different directory, that is the models file, which contains the PDB files. But before writing the awk script, let's have a look into the file and annotate specifically the columns that we need in the file in order to give a condition in order for it to select the particular atom indices. So once again, I open a different PDB file just for you to show that all the atom index are the same for all the PDB files. So as you can see, the first residue has number 2, and the second residue has number 10, the third residue has number 15, so on and so forth. And so what we will do with the awk script is we'll give it a condition that if it comes across the CA, this regular expression CA, or this particular word CA in the third column, which is the column for the atom names, then it will write its corresponding atom index, or let's say the atom numbers, to it. So we can do that by typing in awk followed by a quotation, an open quotation mark, and then $3, which stands for the third column in the file that we saw earlier. So the third column is corresponding to the atom names here. So the condition here would be if the third column is equal to CA, then print the second column, which is basically the atom numbers or the atom indices. So if the third column is equal to CA, it will print the corresponding atom number to it, which is number 2 here in case of the first residue. And so print $2, and we end this bracket here and close the quotation mark. And now we'll have to select the input file on which this awk script will operate, which is one directory back. So just // and locate this directory, which is models out here, and we select one of the PDB models, let's say model 9 that we have opened. So it doesn't matter, you can select any of the model PDBs because all of the atomic indices for the models are the same basically. So model 9.pdb, and then we give it an output file where to write the atomic indices. So let's call it indices.txt. We press enter, and when we open the newly written file indices.txt, which is now written in this particular directory, you will find all the atomic indices being printed as an output in the indices.txt. So that's great. We have the corresponding C alpha atomic indices for all the residues, that is the 42 residues. So you can cross-check back by annotating the line numbers in this file, and you can see that there are these 42 atomic indices representing for each one of the 42 residues of amyloid beta 42. Okay, so we'll feed this indices file as an input to the MD-convert program. So in order to do that, we'll first have this MD-convert written here. So MD-convert is a program that is available as an additional package to the MD-traj Python library, which is a different library altogether. You don't need to know details about this, but just for your information I'm telling. So that's also another efficient Python library that's used for performing a lot of post-processing on the trajectories, be it the trajectories generated from molecular dynamics by running them with GROMACS or NAMD or AMBER for that matter. MD-convert, and then we type in the name of the input file, which are basically input files, in fact, which are all the models in here. So we'll have to go back one directory again. We'll have to go back to the models directory, and then model star. Star is the wildcard entry which we should have for the model numbers, because we have to annotate in some way all the different models to be included together in one field. Therefore, the best way to represent a file that has all the different models together would be by using a wildcard star and .pdb. So I keep all the other expressions that forms the name of the file to be same except for the model number, and that'll allow it to select all the different models together. So it will combine or concatenate all the different models from the input and write it as an output into, let's say we give it a name, models.dcd. So as I said before, the output format for the trajectory would be a DCD format, which is compatible with VMD, and you can open that in VMD as well. And now we'll have to annotate the atomic indices for the C alpha atoms so that it writes only the C alpha atoms corresponding to each of the residues in the models.dcd file. So as an input, we'll have indices.txt. So the flag that you use here to annotate the atomic indices that we'll use as an input is -a. Okay, we press enter and allow the program to run on itself. Okay, so it's done, and you can see that it converted 10 frames. So this 10 frames correspond to this 10 models starting from model 0 to model 9. And so this file, if you open that in the text format, you'll find that it's basically written in binary or ASCII codes. I'll just show that to you, but don't meddle with it, like don't change anything in it, otherwise it will completely mess up the formatting of this file. So if you change anything inside, so you will never be able to open it again in VMD. So as you can see, it's very compressed. So this otherwise, you know, if you write, let's say, 100 frames as into a PDB file, into a single PDB file, that file will be huge in size. But in this case, in a trajectory file, it usually compresses the size of the file by writing them in this ASCII code, or let's say the binary codes. Okay, but this is well read by most of the molecular graphics programs like VMD, Python, and even Chimera for that matter. Okay, so once we have the models.tcd file, that's the trajectory file, the next thing that we'll need is the structure file and containing only the C alpha atoms to it. So I could as well use the mdconvert program to do that, like operate on this file ab42 underscore coil.pdb. That's the extended random coil structure generated by NMR utility web server, again from the Bax group. But I'll show you a different method here. So we'll open that in VMD and specifically select the C alpha atoms and write a new PDB file containing only the C alpha atoms of the 42 residues. So if I type in VMD AB42 coil.pdb, so you see it opens the file, the full structure here containing all the atoms together, including the side chains. So what we are concerned about are only the C alpha atoms. So instead of feeding it any index file, or let's say the file containing the indices or the atom numbers in a text format, we can go directly to file and then save coordinates, and then in the selected atoms you have to annotate for the C alpha atoms, which you can easily do by typing in name. So name stands for the name of any atom, and as we have seen from the PDB file, the C alpha atoms are represented as CA. So name CA, and the file type that will be written is the PDB file, and then we save it, give it name, let's say ab42ca.pdb, and save. That's it. It writes the PDB file with only the C alpha atoms in it for all the 42 residues. So if we close this VMD here and we open that file, that newly written file ab42ca.pdb, in the text format, you'll find that there are only 42 columns, which means these are only the C alpha atoms of all the 42 residues written as an output in a PDB file, in a new PDB file. So we'll use this file alongside the models.dcd file that we have just generated as an input for the programs, for the R scripts, DCCM.R first and then pathanalysis.R. But before going through the details of this R scripts, that is the formulation of the codes and everything, let's first confirm that the DCD file that we have written, the trajectory file that we have written, contains only the C alpha atoms by visualizing it in VMD. Unlike before, where you opened only a single structure in the PDB format with VMD, we'll open the trajectory file, that is the DCD, but you can't just feed in the trajectory file. It has to accompany with a structure file, which is a PDB file that we have written. So we'll open both of them together and see how the trajectory file is written for this amyloid beta 42 C alpha atoms only. So we'll type in VMD AB42CA, that is, we feed in the structure file first, followed by the DCD file, that's the trajectory file, and press enter. So you'll see that it represents here, there are 11 frames, but it doesn't really represent the structure here because these are only C alpha atoms and there's no connection between them. Therefore, traditionally you can't represent them in line format. That's the default format for VMD here. But we'll have to change the representation to a more acceptable format where only the atoms will be shown, the C alpha atoms, which is van der Waals. And as you can see, while I change this to van der Waals representation, all the C alpha atoms in van der Waals representation or spherical representation is shown here, and you can actually traverse along the trajectory and find all the 10 different models. So here it shows 11 frames because the first model is the structure file itself, which is the initial file that you fed it as a structure for the C alpha atoms, and the models formed as a trajectory actually starts from the second frame, that is frame number 1 here, and it goes along. You can see it evolves alongside. So it forms a full trajectory. That is when you actually run a molecular dynamics simulation. So you can see this kind of path formed when you open that in VMD. So it's confirmed that all the C alpha atoms for the trajectory is actually written here. Okay. So we close this and we get on with the R scripts. So the first script that we are going to look at creates a network map from the trajectory of IDPs at different correlation thresholds, that is, at different values of cross correlation between 0 and 1, with 0 being no correlation and 1 being maximum or full correlation. And we'll select different values between that and create the network map or the dynamic cross correlation maps, and look at the community structuring for amyloid beta 42 IDP. And this will all be done between the residues represented by the C alpha atom, and this will be followed by specifically selecting a certain correlation threshold and generating the network map for that and doing the path analysis based on that particular threshold. So we'll go into the details of that, but first let's have a look into the first program, that's DCCM.R. So if we open that in the text format, we'll find all these lines of codes written here. I'll try to go through each of these lines and explain it to you in the simplest manner as possible. So the first thing that we do is we let the program know, or let the code know, that we are running an R script. So the first line, the very first line of the R script would be looking like this, that is hash followed by an exclamation sign and / and then user bin R. So the R program is usually in the bin directory, which is a standard subdirectory containing the executables, or let's say the ready to run programs. And the next line, we load the R packages, that is specifically the Bio3D package, by typing in this command, library Bio3D. And there's an additional package called iGraph. These are all the libraries. So Bio3D and iGraph needs to be preloaded in order for it to include all the functionalities for performing the dynamic cross-correlation network analysis. So in the next line of the code, we read in the trajectory file in DCD format with only the C alpha atoms by storing the file in the variable name files. So the command is list.files, and then you point towards the same directory where you're running the scripts from, and then you give the pattern as star.dcd, because they'll be only looking at the trajectory files in DCD format. And then reading the files with the function lapply. So this is the function lapply, which is further stored in the variable chunks. So the lapply reads in all the files with the command read.dcd and then stores in another variable chunks. Next, we also read in the PDB file, that is the file with only the C alpha atoms for A beta 42, with the command read.pdb and then naming the file in the same directory. The next line in the code calculates the dynamic cross-correlation matrix, or the dynamic cross-correlation maps, which are the correlated motions of two atoms, which are the C alpha atoms here in the A beta 42 peptide. And this is stored in the variable Cij. So I and j stands for the two different atomic indices that are fluctuating with the same frequency within the protein. So Cij is basically calculated with the function lapply again, which is further operated on the function, the inbuilt function DCCM, which is dynamic cross-correlation map, within the Bio3D package. And also it considers the files that are being taken into account. So the chunks, basically the chunks variable stores the DCD file that was read previously. So it does the calculation and generates a map. So it's basically like a contact map of atomic fluctuations, but with the only difference that the cross correlations between the atoms are taken into account as opposed to the direct physical contact between them. So moving on further, we calculate these cross correlations at different thresholds, or at different cutoffs of the cross correlation coefficient, or the correlation coefficient. So as I've said before, the correlation coefficient can range from 0 to 1. So 0 meaning that there's no correlation at all between the atoms, atomic fluctuations, whereas 1 meaning there is significant correlation, or let's say there's full correlation or maximum correlation between the atomic fluctuations. So we calculate these values starting from 0, where we would basically expect that there's no correlation at all, and filter the DCCM map according to that cutoff value, 0.3 and 0.4, 0.5, 0.6, and then 0.7. So we don't reach up to a full correlation, because once you want to have a threshold having a full correlation, there would be very little residue-wide fluctuations based on the C alpha atoms. Therefore, we want to pick a value which is basically reasonable enough in order to record all possible fluctuations between the C alpha atoms. Like if you go too low on the values, it will consider everything. Most of the C alpha atoms between two particular residues will be fluctuating at some point or the other at a zero correlation coefficient, whereas if you go higher up, then less number of atoms will be found fluctuating together until we reach 0.7, where there will be minimum number of atoms fluctuating. So if we go up to a value of 1, then that will mean that none of the atoms might be fluctuating at all. It might lead to a case. So we'll need to carefully choose this value first. So we'll decide on the criteria for selection of a cutoff correlation or a threshold of correlation based on the community structuring. So that's in this part of the code. This chunk of the code deals with the community structuring. So a community is basically the group of atoms which are fluctuating at the same instant, and that forms a single community, whereas another group of atoms fluctuating at a different frequency but also at the same instant will form a different community. And these communities will have a definite network structure. If at two different cross-correlation coefficients, let's say at correlation coefficients 0.3 and 0.4, if you find that the community structuring is the same, that is, the number of group of atoms fluctuating together are the same, and they are basically traversing the same regions within the protein, then we'll consider the 0.3 and the 0.4 to be the reasonable choices for the cross-correlation coefficient, and the network structuring and the path analysis will be done based on that. But first of all, before that, we'll generate few of the plots, like the residue-wise plot. So on the x-axis, you will have the C alpha atoms corresponding to that particular residue, which are basically 42 in number in case of amyloid beta 42. And on the y-axis, we'll have again 42 residues, and we'll plot these against each other. That's why they're known as the cross-correlation map as opposed to just the correlation map. And we'll generate these DCCMs, or the dynamic cross-correlation maps, at different cutoff values for the cross-correlation coefficients. So we'll use this plot function in order to generate these plots. The image type will be basically in PNG format. So R is a very efficient program to plot graphs, and it makes beautiful figures, which you'll see in a minute actually. So let's have a look at the network structuring now, which is basically map of the communities within the intrinsically disordered protein. So in the network, the C alpha atoms of each residue form the nodes, while the degree of correlated motions between residues form the edges of a graph, which are weighted according to their level of concerted fluctuations. So both the correlation network analysis and the community structuring could be performed by this CNA function here. So the CNA function, which is inbuilt within the Bio3D package, will be used to perform this, the community clustering as well as the dynamic cross-correlation network analysis. And so, as I've said before, the community is formed by the different groups of atoms which undergo these concerted fluctuations, or they fluctuate with the same kind of motion, and they are grouped together and they are clustered together, and the communications between them will basically lead to the path, the optimal path and the suboptimal paths, which will further be decided by the network structure at different correlation coefficients, or the cross-correlation coefficient cutoffs or thresholds. So based on this network structuring map, we will be able to decide what value of the cutoff to select in order to further construct the networks and do the path analysis. So once again, just like the dynamic cross-correlation maps, we will use this plot function here in order to plot this network structure, or the network mapping, or the community clustering. And we'll also use the VMD colors. So we'll use the VMD colors palette in order to make the colors according to these communities, the residue-wide fluctuations grouped together. Further down, we'll also plot a minimalized network, which means it will have the minimalistic information so that you can get rid of all the clutter that will be seen through the complete network map that you will obtain from these plot functions. And this minimalistic map will also give an idea about how the network structure is organized in a proper way, in a more clearer way, with the plot function as well. And all these extensions for the images that will be plotted will be in PNG format. Now finally, we'll write down the network attributes. So the network attributes will have the number of nodes and the number of edges and the number of communities that are formed by using the different thresholds, and that will also give us a fair bit of idea in terms of what to select as the particular threshold. So combining all these three informations, we will select a particular cutoff for the correlation coefficient, and based on that correlation coefficient, we'll further construct the network and do the path analysis with the next set of codes, that is the next R script that we'll be using, the path analysis.r. So let's run the script first in order to generate the network maps, graphs, the community clustering, and the network attributes, and make a selection on the correlation coefficient based on which the optimal paths and the suboptimal paths will be generated. So let me close this first, and then we go to the terminal, go back to the terminal, and type in R script. So this is the command that you use to run a R script. That's R script itself. And then type in the name of the program that we're going to run in R, written in R. So that's DCCM.R, and then press enter, and it will generate, it will show you the process as it is going on generating the different network attributes. So beginning from the very first things, it loads the packages and reads in the trajectory, and then it performs this dynamic cross correlation, generates the dynamic cross correlation matrix, and calculates correlations at different thresholds and generates the maps. And then at different weights of the network, it generates the community clustering, and finally it writes down the network attributes in a different file. So it obtains the layout based on the PDB structure that we provided, which is basically the random coil structure for amyloid beta 42, containing only the C alpha atoms, although pertaining to different residues, so 42 residues in total. And so if you do a ls, that is list the files in here, we'll find the number of output files that's written already, and these are all the image files or the figures that are generated in the PNG format. So we'll go through each one of these one by one. So the first file that we'll look at is the dynamic correlation all, which is the map for all the correlations that we get at a threshold of 0 or a cutoff value of 0 cross correlation coefficient. So you'll find when we open this map here in the PNG format, you'll find that it's quite crowded, as we have anticipated before. So the regions in the red are basically the positive correlations that you get between the residues, which are the C alpha atoms representing each of those residues. So there are 42 in number on each axis. So on the x-axis there are 42 residues, and on the y-axis there are 42 residues for amyloid beta 42. And you'll find the specific regions that are undergoing fluctuations at the same time with each other, which are correlated positively and denoted in red, whereas the ones which are anti-correlated or negatively correlated would be denoted in blue. But you see, it's very, very crowded. As I have said before, that at 0 cross correlation, at a threshold of 0, you'll find everything correlating with each other, most of them. So the regions in white out here, which lies between the range of red and blue, would be the regions which are not correlated at all, which are very small in number. So the negatively correlated regions are the ones which are undergoing anti-correlations, which means they are against each other. So they are getting fluctuations in the opposite direction to that of their corresponding atoms, which are fluctuating in the other direction. So they are oppositely correlated in nature. That's why they are negative. And you find this small region here, which might be negatively correlated, which pertains to the unfolding of a protein. But in case of amyloid beta 42, it's already a disordered structure, so it's already unfolded. So further unfolding from that unfolded state would be difficult, and therefore a small region only occupies this anti-correlated residue-residue fluctuation. So on the y-axis, you'll find that this region pertains between 20 and 30 residues, which are basically the C-terminal region, and the extreme end of the C-terminal. So the middle of the C-terminal and the extreme end of the C-terminal are undergoing negative correlations, probably because of a certain fold they were having, and they want to get rid of that fold and go towards the disordered structure more and more. Whereas if you select a threshold of zero point 0.3, which is this guy out here, so a correlation filter of 0.3, you would find that the graph is quite less populated. So at that cutoff, the number of positive correlations that you would find is less than that of the number of positive correlations that you would find without a particular cutoff. Whereas if you go higher up, let's say a cross correlation of 0.4, you'll also find that the number of positive correlations in red are lesser than that of 0.3. Okay, and also another thing is the negative correlations which were supposed to be in blue around this region that you found for the at the cutoff of 0 cross correlated coefficient has disappeared altogether. So it's all about positive correlation now. Further down, let's look at 0.5, and you'll see that the number of correlated regions goes down further compared to that of 0.3 and 0.4. At 0.6, further down, you see these regions which are scarcely correlated have disappeared altogether, which is what we had expected earlier. So this is for 0.3, 0.4, 0.5, and then 0.6. At 0.6, you find that the regions that were faintly cross-correlated, that is represented in a dull red color, would be disappeared, and the cross-correlated motions will have the propensity to go towards more bright red colors here. So last but not the least, at 0.7, you would find most of the positive cross-correlated regions have disappeared altogether, and it's mostly bright red in color. So if you go further up, let's say if you had 0.8 and 0.9 up to 1, you would find that the number of cross-correlated regions between the residues would be still lesser, and you would probably end up with only a diagonal out here for cross-correlation coefficient of 1, which means there will be direct residue-residue contacts, that is the residues that are lying in sequence in the amyloid beta 42 intrinsically disordered protein. So in this regard, a selection of a particular cross-correlation coefficient at which the network should be constructed is imperative, and we'll do that selection based on the network graph or the community structuring that we'll see later on after this. So let me just close these files now and then list the directories again, and you'll find that these minimalized networks and the total networks that we have constructed at different thresholds, we'll have a look into those and decide what threshold to go with for the path analysis. So let's open the one at 0.3 cross-correlation coefficient, that's net underscore 0.3.png, and see how it looks like. So right away you can see all these nodes being denoted by the C alpha atoms for each of the 42 residues of amyloid beta 42, and these are specifically connected by edges denoting the similarity of fluctuations or correlations between them. And then further, a group of nodes or the group of the C alpha atoms would be categorized together to form a community, that is, they are groups of similarly fluctuating nodes here. So you can barely make out the number of communities that are being formed, you know, the shaded regions in yellow and in gray and then in red and some in blue. So the number of communities are difficult to sanction from here. But then again, if you would look at the corresponding minimalistic network for this particular network map, you would be able to distinguish the different communities because it was represent the residues in a group of communities only. So this is for the 0.3 cross-correlation coefficient, and if you go up to 0.4, you would find a very similar network structure. So it's very difficult to distinguish between the 0.3 and the 0.4 for that matter in this case. So let's see the one at 0.5. So there you go. There's the difference. So 0.3 and 0.4 although are similar to each other, when you go up to 0.5, the number of communities significantly decrease. That's mainly because the degree of cross-correlation between those residues or between the nodes increases in number. Therefore, the number of communities decrease to a much greater extent. So as you can see, as opposed to, let's say, 20 communities out here in case of 0.3 and 0.4, you have just two different communities forming groups of residues that fluctuate together here. So the ones in blue and the ones in red, and they are shaded with their corresponding colors in order to represent the communities. Let's move up to 0.6, and you'll find a similar kind of structure, but out here you'll also find, in addition, a very small community formed with probably a single residue, but that shouldn't be taken into consideration, let's say. So we can easily call out that 0.5 and 0.6 are very similar to each other, as they have similar community structuring, although we haven't seen 0.7 yet. So 0.5 and 0.6, they are very, very similar to each other. And once you have an overlay of 0.5 and 0.6, like if you find a similar network structure, then the way to go about it, the way to select the threshold for the corresponding correlation coefficient and go further with the path analysis is to select the one which is lower in value. So we'll go for 0.5 here. So 0.5 has two communities and 0.6 has three communities here. Okay, just for the sake, if you find any significant difference, let's look at 0.7. And at 0.7, you actually find there are more than two communities, or more than three communities for that matter. So 1 and 2 formed by these two previously represented communities, as well as number 3 that was formed at 0.6 cross-correlation coefficient. That's residue number 10 and 8. And then you have another community. That's the fourth community. So this is like 9 to 15. So that's basically the N terminal. And then you have 16 until, let's say, this goes all the way around. So you have a bit of N terminal here in the red community as well. And then you go up further up to number 30, which is closer to the C terminal. And it also includes the central hydrophobic domain. This is all for the random coil structure, because in the random coil it's in the constant fluctuation, and even the ensemble containing the 10 different models would be in a state of constant fluctuation. That is, they would be enough different from each other in order to reduce this kind of a complex network model out here. That's why it's so difficult to model IDPs in the first place. Alright, so we don't find the similarities of 0.7 correlation coefficient community structure with that of 0.6 or 0.5, but we find significant similarities between 0.5 and 0.6 itself, which are these two structuring here. So we'll go ahead with the lower number, that is 0.5. But before doing that, let's have a look at the minimalistic network structure. So if I open in a similar way the minnet, that's at the first one at 0.3, and as you can see, it's a total clutter out here. So even if you zoom into it, you'll find that there are at least 21 different communities formed with groups of residues or groups of nodes that fluctuate in the same frequency. You would expect a similar kind of structuring in case of 0.4 as well. So yeah, 0.4 community structuring is very similar to that of 0.3 here. And then if you go higher up, that is 0.5, you get just two communities, as we had seen previously from the complete network structure. And then you go up to 0.6, and you will find there are three communities formed with the groups of residues. Okay, and there's communication between them as well. So these are the edges between the communities. So 0.5 and 0.6 are very close to each other, with only difference is that one community between them, and that single community is also formed with two residues only, so that's not that significant. So we can boldly go ahead and select 0.5 as our threshold correlation coefficient for the path analysis. So before that, just let's have a look at point 7 for the community structuring, and you'll find 1, 2, 3, 4. So 4 communities are formed, as we saw from the full structure as well. Okay, so for the next part of the analysis, we will be going ahead with the point 5 threshold for constructing our networks and then doing the analysis of optimal and suboptimal paths, which is running the script pathanalysis.r. But before that, let's get a quick glimpse of the network attributes, which are generally the summary of the networks, that is the minimalistic network and the full network that we have generated until now, which contains the information on the number of nodes and the communities and the edges. So you'll find that for point 3 cross correlation coefficient, the number of nodes are 42, as for all the other cross correlation coefficient threshold values, because there are 42 residues which are represented as the C alpha atoms for amyloid beta 42, and the corresponding edges for the point 3 cross correlation coefficient is 639. So that's a huge number, that as you found from the community and the network structuring as well. And the 42 residues are exactly divided into 21 community nodes, which are further connected by 176 edges. These are the edges between the communities. So 2 communities form one edge here. Whereas if you move up to point 4, it's a very similar, in fact it's the same network structure that we have. So point 3 and point 4 are very same to each other, but this is huge in number, the number of community nodes that we have and the number of edges. So we can't really go ahead with picking any one of these values, or let's say the lower value point 3, because this is a complete clutter. So the main idea of doing the network analysis is categorizing or grouping them together into communities such that you end up with a reasonable number of communities, not this bigger size. Okay, so if you move up to 0.5 again, we'll find the number of nodes do not change and the number of edges decreases between the nodes, which means that it is considering the residue fluctuations to a lesser extent, and so the standards has been set to a higher level at 0.5 as opposed to 0.4 and 0.3, and the number of community nodes decreases significantly, which means the residue fluctuations could be represented by 2 separate groups at the most, and these are connected by just one edge, as you saw from the minimalistic network as well. So if you move up to 0.6, you'll find 3 nodes and 3 edges, whereas the number of edges connected between nodes, that is the C alpha atoms of the 42 residues, is also decreasing, as you would expect. And further down at 0.7, you find that the number of edges also decreases further from 0.6, and the number of community nodes, by the way, increases, which could be mainly due to the fact that the more stringent grouping criteria could render more number of community structures, which are further connected by 6 edges here. So we are in our own right to select the criteria for correlation coefficient as 0.5 for a threshold. Let's have a quick look at the second R script that we'll be using for this dynamic cross-correlation analysis. That's pathanalysis.r. So if I open this script in GVim, that is in the text format, you'll find that the first few lines of the script are basically the same as that of the previous script that we have seen. That is the script for DCCM.r. So you first of all load up these 2 libraries, Bio3D and iGraph, and then you load the files of the DCD in chunks and keep it in the variable chunks itself. And now, as opposed to the last time, you just load the PDB as the whole PDB, as in containing all the atoms, as opposed to just the C alpha atoms. The reason being, we will basically make a trace of the plot of the paths on top of the whole structure that we started off with, like in the coil structure that we initially generated from the NMR utility by the BACS group. So that'll give us an idea about how the paths are traversing, the optimal paths and the suboptimal paths, how they are placed on top of this structure actually. So the next line again is basically generating the cross correlation matrix. So you store the values in the variable Cij for a cross correlation of at the threshold of 0, or without imposing any kind of restrictions, or without giving any kind of cutoff for the cross correlation coefficient. And then, as we have selected earlier from the earlier script and based on the network structure and the community structuring, you select zero point 0.5 as the cross correlation coefficient at which you calculate the cross correlations, and you generate the network map as well with the community structuring and everything. So CNA is the function for generating the network map again. And based on this network map, you will have the full path generated, which you can visualize in VMD, which you will see in the next few lines. So the next lines in the script, starting from the node centrality until the printing of the shortest paths and the path distances, is the chunk of code which deals with the path analysis and a specific terms pertaining to the graph theory. So the first is the betweenness centrality or the node centrality, which basically measures the expansiveness of nodes. That is the extent to which a node lies on paths between other nodes. That is, nodes having high betweenness may influence a network by controlling passage of information between the nodes. This is calculated by the betweenness function, which is this one out here, and then stored in the variable node.betweenness. Further, this can be plotted in the graphical form by using the function plot, which we will see later on when we open each of the outputs that are being generated by each of these chunks of codes. This node betweenness will give you an idea about the expansiveness of the nodes at particular correlation coefficient of 0.5. That is the network that is generated at correlation coefficient of 0.5 out here. So as you can see from here, the plot will basically feature on the x-axis the residue number and on the y-axis the centrality function. So, and it will be in the form of a histogram. So that's why it's given the type as H here. Okay, so moving on, the next thing that we will calculate or compute is the suboptimal paths. So the suboptimal paths are the number of paths that are traversing between two specific nodes around here, and we have to define those two specific nodes. So which are the residues of interest in our case, and which are the residues that we want to focus on. We pick those two residues and then compute the paths between them. So there's an optimal path and there's a suboptimal path. So the optimal path is basically the shortest path between the two residues. So it will be the easiest path to go from one node, your selected node, to the other node. Whereas the suboptimal paths are the number of other possibilities which might not be the shortest path, but these are the number of paths that might be possible to traverse from one node to another node. So in this case, we are computing the path for the whole protein, which basically means the first residue that we will be focusing on as the node, which is the C alpha atom for the first residue of amyloid beta 42, is number 1 itself. That's on the extreme end of the N terminal. And the other residue, which forms another node, is the C alpha atom of the 42nd residue. That's the extreme end of the C terminal. So these two residues are known as the source and the sink, respectively. So we will basically calculate about 500 paths between the source and the sink, which means during the course of the dynamics or the molecular dynamics simulation, or even in case of the ensemble that we generated out here. So the 10 different models will have 10 different features, and we will basically be able to design what is the path that is undertaken from first residue to the 42nd residue, that is N terminal to C terminal, in order to evolve or traverse through the 10 different models. So the number of cores that we'll be using for this job is 4. So it depends on your computational capability and everything. And then again, we'll use this function CNA path, which will basically store this whole thing within the PA underscore whole variable out here. So once we have this, we'll keep these paths in a list, let's say. So this all together, this 500 paths, and we'll put this together in a list which will be further stored in the variable PAS. Then we dump this whole feature that we got as an output from here into this text file pa.txt, which means it will write down the specifics of the paths from residue number 1 to residue number 42. that we have generated. So in this case, append is equal to true means if there are additional paths that you're calculating. So in this case, we are just calculating between just two different nodes. But if you want to include additional nodes, like let's say somewhere in between, like central hydrophobic domain to the C terminal, which is let's say residue number 17 to 42, or the N terminal to the central hydrophobic domain, which is residue number 1 to 17 out here, then you can include additional paths and store them in a variable, and it will keep on appending on top of the ones which are already written out here. That is the path variables or the details of the path. Next, we move on to the main lines of codes for path analysis, which are the path length distribution and the node degeneracy. So I have used an acronym for this for generating the plots. So for path length distribution, it's PLD, and for node degeneracies, it's ND out here. So path length distributions for the designated source and the sink residue pairs will give the probability densities of residue paths, that is between the two nodes out there. So, but the length here does not really correspond or does not really translate to actual geometric lengths. So it gives you an idea or an estimate about the coupling strength between the source and the sink residue pairs that we have used, in this case 1 and 42 out here. Whereas the node degeneracies quantify the number of paths traversing from each node or highlight the densely connected nodes. So the difference between the node degeneracy and the betweenness centrality that we have calculated before is basically that betweenness centrality deals with any node which acts as a bottleneck, as in it acts between a connection between two other nodes, and the node degeneracy is the connection that are arising from a single node in order to quantify the density of each of the nodes. And so the nodes with the higher densities would basically signify the busy nodes, and most of the paths are actually traversing through that particular node out there. The next three lines of the codes are nothing but just a repetition of what you have already here, but ideally you would have source and sink residue pairs pertaining to different regions. I just have two different nodes annotated, that is the very first node and the 42nd node, which pertains to the N and the C terminal. Therefore you find a repetition of this, but in general I had different regions annotated which will be plotted in black, purple, red, dark green and orange. So the node degeneracies and the path length distributions will be plotted in these different colors for different regions in the first plot here, whereas in the second plot only the node degeneracies and the path length distributions for between residues 1 and 42 will be plotted out here, because I just wanted to show you the path analysis for one pair of residues or one pair of nodes, the source and the sink residue pairs of the first and the 42nd residue. Okay, so moving on, we will view the paths now in the VMD with different color annotations for them. Okay, so we again use the function CNA path out here that we have used before as well, and the path for which we had stored previously in a variable PA underscore whole. So we'll use this inside the function CNA path, and then we'll ask VMD to traverse or plot the path. You will see that in a minute when I run this program, run this script. And these are the specifications for the paths, especially the colors are in dark green and red. So it will be within the range of the dark green and red, which means the paths that are not being traversed occasionally or the paths that are not frequent enough will be colored in dark green, whereas the paths which are highly populated will be colored in red out here. Okay, and the launch is false because once we run the program, we don't want it to launch the VMD right away. We'll do it manually. So again, this makes an output file named this, which is vmd.cnapath.pdb. So we'll just rename this file to pa-whole.pdb, and pa-whole.vmd is actually the state file of VMD, which will be used to superimpose or plot the paths on top of the structure that we have as pa_whole.pdb, which is basically the structure that we read in as an input out here on top. Okay. And then finally, we print the shortest path and the path distances. So the shortest path again is basically the optimal path. You print the shortest path into a text file, which will also be plotted out here. So this particular plot in VMD that we'll be generating will have all the paths together, including the shortest path or the optimal path and the suboptimal paths. So let's go ahead and plot all of these and have a look at the outputs. So let's run this script then and have a look at the result. So our script pathanalysis.r as before. And as you can see, it's running. It might take a while to run this. So we'll wait for this and wait for the results. And once we have the results, we'll see the output here by listing all the files. Okay, so it's complete now. The script has been run now, it reached 100%, and it printed all the paths as well. So we are going to have a look at the outputs that it generated, that is the different plots that we can find, as well as form a plot with that of VMD out here. So if we list the files, then we see all these newer files that have been written. So these are the ones that were written previously by the DCCM program, the correlation filter and the minnet and the net here. Whereas these ones, the betweenness 0.5.png and the pa.txt and the pa whole, the three different files, one pdb png and the vmd state file, as well as the pld nd.png and the shortest path, these are the new ones that have been written. So let's first have a look at the betweenness centrality plot. So if we open this, on the y-axis you find the centrality values out here, that is the number of paths that are traversing through that particular node, forming the bottleneck, that is that particular node is connecting two other nodes and it acts as the central node of connection. It bridges the other nodes together, and the population of that would be denoted in form of a histogram out here. And so on the x-axis you find the residue numbers or the residue IDs here. So that's from 1, starting from 1 to 42 for amyloid beta 42. So the first thing that you notice is that the residue number 29 out here forms the central hub as it hits the maximum value, almost reaching the number of paths around 140. So this is a non-normalized value. So the total number of paths adding up for all of these histograms would be around 500, because we selected a maximum of 500 paths. So this one right here almost reaches up to 140, followed by the residue number 41. So these two residues are actually around the C terminal. So the C terminal can be said to form a central hub in this network of paths, that is more number of edges or more number of connections or more number of residue correlated residue fluctuations will pass through this C terminal region. And this is further followed by this residue number 28 as well, and then you have one residue within the central hydrophobic domain, that's the number 18th residue. So it could be said that the betweenness centrality is formed by mainly the central hydrophobic domain and a few residues in the C terminal region. So that'll give us a good idea about density population of paths that are traversing through the different intrapeptide regions in the amyloid beta 42 IDP. Okay, so the next thing that we'll look at is the path length distribution and the node degeneracies. So I'm just going to open up this file here, which is the pld_nd.png, and the corresponding text file to it, which basically gives you the path length distribution and the node degeneracies in the text format. That is, it gives you the actual numbers in quantitative values. So first thing, we look at the graph. So as you can see, the path length distribution has the probability density on the y-axis, and on the x-axis it will be given the path lengths. Again, these are not the actual physical path lengths, but rather the weighted averages of the different edges that form, that is the different connections that are being formed between nodes. And so you can see that it gives you an idea about the strength of coupling between the two nodes that you selected as the sink and the source residues. So the maximum number of the weights that you find here is basically around the higher numbers. So the higher path lengths have greater number of weights, which means that the longer distance of separation which is our N-terminal and C-terminal, have greater weights of path length. That means maximum number of paths are passing through that region. So that could probably be the shortest path. We'll see that later on when we actually have a look at the shortest or the optimal paths. And the next thing that you have is the node degeneracies, which is basically the number of edges that are passing through each one of the nodes. So you see the N terminal is highly populated with the edges or the connections, whereas the C terminal is also highly populated, but the central hydrophobic domain, for which we found a particular bottleneck from the betweenness centrality, is not actually that much populated. So the reason could be that although it forms a bottleneck, that is, although it allows passing of different paths and joining between two different nodes, but it doesn't really give rise to a number of edges. Therefore, we are anticipating that the connection would be maximized within the N-terminal region, that is the first few residues, and the C-terminal region. So this is starting from position 1 until position 42. And these are the total number of paths. As you can see, the total number of paths are 500. So this is a non-normalized value. So these values are not normalized. So moving on to the text file, you will see that the numbers are indicated here. So the total number of paths again is 500, whereas the path length distribution shows the minimum number of paths actually passes through lower weight values, and the maximum number of paths that is allotted to the maximum weights here, that's 0.516 and 0.587, is actually 311, which means at greater lengths of connection, there will be the maximum population of the edges, which forms the paths. When looking at the node degeneracy table, again you find that a score of 1, so it's a value between 0 and 1, and you find that a score of 1 is allotted to the first residue, whereas a score of 1 is also allotted to the 42nd residue. And all the residues in between the N-terminal and the C-terminal have a values between 0 and 1. So we can easily anticipate that 1 and the 42 would be the most probable shortest path length or the optimal path length that might be formed. We'll see that in a minute. So another additional information is, although you saw in case of the graphical representation of node degeneracy that this is a non-normalized value, that is, you can find the total number of paths here, whereas this guy out here is actually the normalized value. That's why you find these values as 1. So 1 corresponds to a total of 500 paths, whereas all the other values lesser than 500 would be between 0 and 1. Same with residue number 42 as well, which has got this value of 1. Okay. Now let's have a look at the shortest paths. So in the text format, if you open the shortest paths, the file that was written previously, you'll find that it exactly matches our evaluation and anticipation from the node degeneracies, the path length distribution, and the betweenness centrality. So you see here, the shortest path or the optimal path is traversed from residue number 1, that is the end of the C-terminal, up to residue number 33. So the shortest path is between these two residues, 1 and 33, which forms the very end of the N-terminal and part of the C-terminal here, which further goes down until the end of the C-terminal, because that was the sink residue that we had selected. None of the other residues in between form the part of the shortest path or the optimal path, which means that in a disordered state of amyloid beta 42 and in the absence of any secondary structure, an ensemble of the intrinsically disordered proteins would basically produce the shortest path between the edges of the N-terminal and the C-terminal. So we'll finally have a plot of this in VMD, that is, we'll plot this shortest path as well as the other paths together, the optimal and the suboptimal paths, that is all the 500 paths, and see the weights of the edges that will correspond to the maximized path lengths there. Okay, so just going to close this here and open the file pa_whole.pdb first, along with the state file which has the path information there. So that's pa_whole.vmd. If you press enter, you'll see that it calculates all the different paths out here that are to be plotted in VMD and then plots them on top of the disordered structure in the new cartoon format. Okay, so the state file already has this information about the different path lengths and the path information there, which you can also cross-check by going to graphics, and when you go to the representation, you'll find that these representations are automatically saved inside the state file that we had selected, that is the file with the extension .vmd. Okay, so it selects residue 1 and 42, which are the source and the sink residues out here. All right, so let's have a quick look into the different paths. So you can see it's a clutter. You'll have to categorize these paths based on their thickness, as well as their lengths, as well as their colors. So the colors, as we have set it before, like the prominent paths would be set in bright red color, whereas the non-prominent ones would be set in dark green color. So you find that the dark green color paths are also very thin, whereas the dark red color plots are thick in size. So if you zoom in further down, so these are the N terminal and so these residues which are represented in licorice is the N and the C terminal respectively. So let us set this. So this is the N terminal and that's the C terminal out there. So that's residue number 42 and this is 1. So let's set this in a manner that the N terminal is on the left and the C terminal is on the right. Now, if we bring this towards the center, and if you want to have a look from here, so the path actually travels directly from the N terminal to the end of the C terminal, which you can appreciate by looking at the thickness of the path. So most of the thick paths out here, and amongst these, there will be one optimal path as well, which is the shortest path, and that's the thickest path and brightest red in color. Okay, so all the other paths are actually suboptimal, and they would always equal to, or the total number of paths would be equal to 500 in this regard. Okay, we constructed our model network and we selected a particular threshold for the correlation coefficients. We did the path analysis, we did the node degeneracies, the betweenness centrality, the path length distribution, and then we looked for the optimal and the suboptimal path. And then we came up with this plot where you find that the N terminal and the C terminal forms the optimal path, which means this transient structural propensity of having secondary structures in different regions in between these N terminal and the C terminal disordered state would depend upon the extensiveness of the ensemble. So a predominantly disordered state would always produce the shortest path between the N terminal and the C terminal. All right, so that's it about the dynamic cross-correlation network analysis with the R package Bio3D.